very brief invitation to algebraic geometry, what it's all about. Then I'll go into the uniform ideal containment problem that guided my thesis work. And I'll state one of the main results from the thesis, which has ties with convex geometry. So in this talk, all of the rings that we'll consider are non-zero and commutative with identity. So to talk about algebraic geometry, I have some quotations in mind. One by Sophie Germain that says that algebra is nothing more than geometry in words, and geometry is nothing more than algebra in pictures. And this holds out a lot of currency in algebraic geometry. And another quote by the late geometer George Kemp goes something like this. Algebraic geometry is a Mediterranean menagerie between the Greek geometric tradition on the one hand and the Arabic algebraic tradition on the other. I think these quotes are dope. So I like them a lot, and I even used them in my first chapter of my thesis as a way to engage algebraic geometry. So there are pictures like this yin-yang symbol that I drew using Wolfram Alpha. So you can think of a bunch of different cases of algebraic geometries and study their singularities and things like that. So the main object of study in algebraic geometry is algebraic varieties. And these are the common zero sets, either in Rn or Cn for now, of systems of polynomial equations. So I could have K equations and consider all of the common 0 points of those. When we have one non-constant equation, this is known as an algebraic hypersurface. So typically in drawing pictures, we work over the real numbers, even when we want to consider complex algebraic geometry. And we work over the set C of complex numbers and citing results in this area. So we could ask questions about what are the Hilbert-Snell-Zelensatz and the Hilbert Basis theorem over C, and why should we care? And I'll summarize this with the vanishing set of the equation x squared plus 1. So since this is a quadratic equation, we would normally expect there to be two solutions to this equation, given the degree. And while that turns out to hold some merit in C, in R, this set is empty. So it doesn't agree with our intuition. Whereas over C, it agrees with our basic intuition about the degree of a polynomial. It should have degree many solutions. So the Hilbert Basis theorem, well, the Hilbert-Snell-Zelensatz says that it gives a condition for your algebraic variety to be non-empty, fundamentally, to have a solution or a root. Whereas the basis theorem, Hilbert's basis theorem, says that even if you consider the infinite, a case where you have infinitely many polynomial equations, you can always find a finite subsystem of your equations that give you the same algebraic variety for free. So within an infinite collection, a finite subcollection will always generate the same algebraic variety. So that built-in finiteness is nice, and we consider that in drawing pictures and things. So we could talk about algebraic curves and surfaces. So dimension 1 and dimension 2 examples. And with pictures in these low dimensional cases, we can come across definitions for the dimension, whether a variety is irreducible versus reducible, and when it's smooth versus singular. So the figure here has 7 examples. And of these, 3 varieties are smooth and irreducible, and the other ones are singular. And of the latter 4, 2 are reducible, and only one has a one-dimensional singular locus. So you have the unit circle and the unit sphere, and then also this one that looks like an ice cube. And those are going to be smooth cases, whereas the case of singularities remains for the other 4. And the one that has a one-dimensional singular locus is the one with the coordinate planes. So the 3 coordinate planes, like the xy plane, the xz plane, and the yz plane, that one has a one-dimensional singular locus, and it's just the union of the coordinate axes. it turns out that if you have a smooth algebraic variety and you intersect it with even another smooth algebraic variety, the intersection points are singular. And then here's a double funnel cone. To see more examples of algebraic varieties, you can look at Herwig-Hauser's gallery of algebraic surfaces. So he has a whole listing of a bunch of different types of algebraic surfaces where you consider the real points for the solutions. And they can look pretty exotic, even when working in R3. So there can be a lot of eccentricity to the morphology of these varieties. So there's the ding dong, Eve, helix, and the octong, and a bunch of other ones, many more than I had captured with the camera on my phone. But yeah.
There's a question, Robert, in the chat about what is the flirt one?
This one?
I guess I'm more meant why it's called flirt. Like, I understand why the ding dong is called ding dong and Eve sounds a little like helix is helix. Why is the flirt one called flirt?
I don't know. Maybe they think of the singularities as forming some sort of kissing action. I don't know this backstory behind why it's called the flirt, but I could believe that. But yeah, these are some examples in Herwig-Hauser's algebraic surfaces gallery, which you can find via Google.
Are these names actually used in the literature?
I don't think so. I think these are not quoted in the literature. That I have never seen.
Sorry, it's a very tangential question, but it's kind of fascinating to think of having ding dong in a mathematical paper.
Yeah.
They're usually the authors.
But yeah, I haven't seen these names myself in any algebraic geometry literature. It would make for lighter reading. So, okay. So there's a relationship between varieties and radical ideals inside of rings. So for starters, we'll consider R to be the ring of complex polynomial functions and n complex variables, which can be viewed as functions from Cn to C. And given an algebraic variety V inside of Cn, each F in R can be restricted to a function V to C. So we can describe this as a surjective ring homomorphism, where the coordinate ring CV of V consists of all the functions you obtain by restricting polynomial functions to V. And there's this natural surjective ring homomorphism called restriction to V. So you have this mapping and you just take F and map it to its restriction function. So we can consider the kernel IV, and that's the set of all the polynomial functions that identically vanish on V. So this gives an isomorphism between CV and this quotient ring by IV. And this is just the first isomorphism theorem by Noetherian. So the defining ideal IV of V is always a radical ideal. So if you have F to the n belongs to IV for some positive integer n, then in fact the original function belongs to IV. And that's not too bad to prove, basically using the fact that a field like C is also a domain. So if it's identically zero at those points, then you can just assume that the original function is zero at those points. Okay. So one of the more important features at the beginning of an algebraic geometry course is the affine no-Stellensatz correspondence for a variety V over C. So we can consider the coordinate ring, and it has this presentation in terms of IV. And there are bijective correspondences between the geometry aspects of V and the algebraic aspects of CV. So algebraic subvarieties of V correspond to radical ideals inside of the coordinate ring CV. And In particular, irreducible algebraic subvarieties of V correspond to prime ideals. So yeah, without going into too much detail about what irreducible should mean, basically, if you think about a connected variety, then you're not too far off to how to think about an irreducible one. I think of them as examples that you don't have to lift a writing utensil in order to draw completely. In particular, under this correspondence, points in V correspond to maximal ideals. And so P corresponds to IP, just the set of the functions that vanish at P. So it's natural to talk about the dimension of these varieties, whether it's a smooth or singular curve or surface. And there's a corresponding notion called the Kroll dimension of CV, and these match. So we can talk about the dimension of a ring, and under this correspondence, you have this relationship between the dimension of a variety and the dimension of its coordinate ring. Under this correspondence, V itself being irreducible corresponds to the coordinate ring being a domain. And when V is smooth, that corresponds to the coordinate ring being called a regular and affine regular ring. The way I describe smooth to people is that when you draw a path on your variety, there's no way to draw a path that doesn't look V-shaped somehow. You can always find a turning point inside of the variety. So those are singular points. And one thing to note is that this coordinate ring is a Noetherian ring, and that means that all of the ideals in the ring are finitely generated. Okay. So that's more or less what I wanted to say about algebraic geometry. In this next section, the main questions are: what are regular and symbolic powers of radical ideals? And what is the ideal containment problem? So with regular powers of an ideal, I think about that as a generalization of doing FOIL in K through 12. So the idea is, do you have an ideal I and R? And the nth regular power IN is just the ideal generated by an n-fold product of elements of I. So if you have two generators for your ideal, then I squared gives you all of the products of two with repetition allowed. Those will form the generators of I squared. And more generally, when you have T defining equations, so you consider R linear combinations of those elements Fi, and In is just all of the R linear combinations of n-fold products of your equations F1 through Ft. So repetition is allowed. So to get a geometric interpretation, if R is the polynomial ring in n variables, n complex variables, and MP is the maximal ideal of functions vanishing of T inside of Cn, then MP to the n is going to be the set of ideal, the ideal of functions vanishing to order at least n at P. So given an irreducible subvariety of Cn, and P the corresponding prime ideal in C x1 through xn, Pn is contained in the ideal of functions vanishing to order at least n at every point P and V. And a question that one can ask is, are these two ideals going to be equal, Pn and this ideal of functions that vanish to order at least n?
What do you mean by functions vanishing to order at least n?
So if you apply like the derivative rule for products of functions, then basically there are zeros of the function that even if you differentiate like n minus 1 times, the resulting function still vanishes at that point P when you evaluate it.
Oh, gotcha.
So,
it's like the normal.
Yeah, so it's like doing that rule in Calc 1 of just taking derivatives of products of functions, there's going to be some vanishing even at the nth or the n minus first derivative. So yeah, some zeros appear no matter how many times you differentiate, they still come up. But yeah, that's what I would say for that question. So in this setup where we have P any prime ideal of R and V being the vanishing locus of the ideal P as the corresponding irreducible algebraic variety, the nth symbolic power of P for n a positive integer is going to consist of all of the polynomial functions that vanish to order at least n at each point of V. And another way you can represent that is as an intersection of nth powers of the maximal ideal that contain P. And this uses the fact that C is an example of an algebraically closed field. It turns out that this definition will also work for radical ideals, not just primes. But for the main question of the ideal containment problem, I'm just going to talk about it for prime numbers. I mean, prime ideals. But yeah, that's one description. And so for any positive integer pairing A greater than B at least 1, the first symbolic power will coincide with the prime ideal itself. And we have PA is contained in P symbolic A, is in turn contained in P symbolic B. And in fact, P symbolic A is equal to PA for all A if V is smooth. And V's ideal inclusions can be strict. So it's possible to have strict inclusion instead of equality. So I'll give an example of this. But first, I want to consider what the more commutative algebra definition of a symbolic power is at the level of a prime. So if we fix a Noetherian ring R, so all the ideals are finally generated. And for a prime P inside of R, the nth symbolic power of P is written this way in the middle with localization notation, the ring localized at a prime P. It consists of all of the ring elements such that U times F is inside of the ordinary nth power for some U that's in the complement of P inside of the ring. So in the theory of primary decompositions in commutative algebra, we would say that this is the P primary component of P to the N. It's the smallest P primary ideal containing P to the N. P primary just means that the radical ideal of your ideal is P. An M primary ideal for a maximal ideal would just be some ideal whose radical is M. So it generalizes that relationship. So we note that the zero symbolic power coincides with the regular power, and that's just the whole entire ring. It's the unit ideal. And again, P to the first power is going to be P. So in this example, I consider a hypersurface ring where we consider the relationship y squared equals xz. So I have P being generated by 2 elements inside of this ring, the residues of those elements. And then I expand out what P squared should look like based off of FOIL. And then we use the relationship between y squared and xz and replace that element inside of the generating set. And this is strictly contained in the ideal generated by just x. And in turn, this is not only contained in the P symbolic square, but in fact, the principal ideal is equal to that symbolic power of P. And we get these relationships because Z is inside of R minus P. And ZX is going to be the y squared, which is in P2. So that's how these relationships work from P squared up to P symbolic square. So this is an example where the two notions are meaningfully different. Before I go on, are there any questions that in mind for anyone? Okay. So it looks like we're 22 minutes into this. So this is the part that was supposed to be introductory anyway. So that's good. So the uniform idea of containment problem will be this slide. So we know that by definition, the nth regular power of a prime ideal is contained in the nth symbolic power for all n. In that case, you can take the element u to be the multiplicative unit. Then you're just talking about f being in P. So we have this containment for all prime ideals P and for all values of n greater than 0. And we can ask about unearthing converses to the statement. When is a given symbolic power contained inside of a regular power? So given a prime ideal P inside of our Noetherian ring R, you could ask, is there some integer D depending a priori on P such that P symbolic dr is contained in PR for all R greater than 0? So this is like a linear problem, a linear growth problem. And another question, which I would think of as even better, is there an integer D that depends only on the ring structure of R that works simultaneously for all prime ideals P inside of the ring? So we move from something depending a priori on P to something depending only on fundamental structure of the ring. And if we know that we can do this, then the next question is, can we describe explicitly what this value of D is? That's more satisfying than just having an existence result.
Sorry, excuse me. Would it be possible to see the definition of the symbolic power again? Thank you. Thank you.
Sure.
Thank you.
So yeah, this is the definition of that. So we want to consider cases where a given symbolic power will be known to be contained in a given regular power. And it turns out that asking that question for symbolic powers generally, where you don't specify linearity, it's actually equivalent to the linear statement that I made.
Is this definition the same as the definition of where it vanishes to order greater than or equal to n at all points of the ideal or of the variety corresponding to P?
Yes, in the polynomial ring case that I was considering. That
I see. Okay, so this is the generalization to other rings.
Yeah, this is a generalization to Noetherian rings generally.
Thank you.
Mm-hmm. So yeah, this is how commutative algebraists tend to think about symbolic powers, but at least in the polynomial case, this relationship will coincide with the definition in terms of maximal ideals. Yeah, this is this result for the polynomial ring case is known as the Zariski-Nagata theorem in the literature. So yeah, there's a lot of interest in like finding versions of this Zariski-Nagata theorem in Noetherian rings more generally than just polynomial rings. And there's a paper by I think it's Alessandro De Stefani, Eloisa Grifo, and Jack Jeffries that gives a nice new relationship that is like a new Zariski-Nagata theorem for so-called smooth integral algebras. So there's interest in finding relationships like that, even in rings that are more general than a polynomial.
What part of that definition, like, for what part of it do you want the R's Noetherian?
Basically, we're applying the primary decomposition results inside of commutative algebra, and those behave best when you work inside of a Noetherian ring. So that's the reason why we would want to consider this for Noetherian rings. The behavior of theorems themselves and what the theorems look like, that they are nicest when your ring is Noetherian. But yeah, this is like Pn will be an intersection of a bunch of ideals that are all primary to some prime P. And the unique components of a primary decomposition correspond to the so-called minimal primes of the ideal. So in the case of P, the radical being the prime ideal itself just means that there's a unique P primary component for Pn for any n. Are you good with the definition?
Yeah, thank you. So I guess if you picked a non-Noetherian ring, that you're saying that the P primary component wouldn't necessarily be unique.
Yeah, I think of Atia McDonald talks about, the Atia McDonald book on commutative algebra talks about primary decompositions even in the non-Noetherian case, but the theory looks just a lot nicer when you consider a Noetherian ring. Okay. But yeah, this is a linear rendering of the ideal containment problem. So we want to study the set of tuples, integer two tuples, such that Pn is contained in P symbolic n is contained in PR. But solving this for all values of R is the same thing as doing a linearized version of it, with the slope depending, hopefully, just on the ring structure and not necessarily on the prime ideal itself. So in saying that, the sense that maybe an algebraic geometer might have about these symbolic powers is that as the singularities of the corresponding irreducible algebraic variety become worse on the spectrum of all singularities considered in algebraic geometry, the larger the D value has to be in order to get this containment. So they would expect that if you're considering a subvariety of a given codimension, and you know that the singularities are really nasty, then that should increase the value of D necessary for this containment in the first question. But it turns out that that's not true. So what we have here is I'll use the coordinate ring of an algebraic variety. And if X is smooth, then the dr symbolic power is contained in the PR regular power for all prime ideals P. And we can take D to be the maximum of 1 and the dimension of X minus 1. And this result was proven by Lawrence Ein, Robert Lazarus-Felt, and Karen Smith, my advisor, back in 2001, over fields of characteristic 0. So they especially worked with C. And then Coxer and Hunicke came in and they proved the same result, where you can replace C with any field. You can consider a so-called affine regular ring over any field, and the same result is true. So it's a vast generalization on the Ein-Lazarus-Felt-Smith theorem. We also know that when the singular locus of your variety is 0-dimensional, so it's a non-empty finite set of isolated singularities, then the same question still achieves a uniform answer, but the result that they prove is not constructive or effective. It doesn't tell you what D is going to work. It just tells you that it exists. So there's been a lot of attention in recent years, in the past decade between 2010 and 2021, to try and figure out, whenever you have an isolated singularity or something with isolated singularities, what is the D value that will actually work, an explicit number. So there's been work on like Veronese rings and Segre products of rings, and the homogeneous coordinate ring of something like the Plücker embedded Grassmannian. And in all of those cases, it was initially not known that what the D value is going to be. So for a while there, almost a decade, there was no result that said explicitly what the D value could be for like a Segre product of two polynomial rings. Now more recently, in the past few years, like the past 3 years, there started to be answers to those questions. So we're knocking out case by case different ways in which you can get an effective multiplier explicitly, not just the existence result of unique capacity validation. So those are the most general results on this problem. You have either the Einleitungsfeld-Smith theorem in the smooth variety case, or you have that the singular locus is zero dimensional, and then it's still solvable, but by what? So the question that one could ask is, what can we say if the dimension of the singular locus is positive? So you have non-isolated singularities, but maybe X is still a nice variety in some other way. So I think about this as a quid pro quo. If we focus on a particular class of prime ideals inside of the coordinate ring, can we say what the D value is for those? So this is like a sort of partial result on uniform symbolic topologies. At least that's the name of the problem in the commutative algebra literature, uniform symbolic topologies. So maybe you can get a specialized uniform symbolic topology result if you focus on a particular class of primes inside of the coordinate ring. So this is the question from before. And one of my main thesis results is that if you consider the coordinate ring of a normal affine toric variety, X, then there exists a value D depending on data on R only, such that the dnth symbolic power is contained in Pn for all positive integers n, and all monomial prime ideals P and R. So moreover, we can give a recipe for computing D via linear algebra. So I'll try to explain briefly what toric varieties are. So we can consider the so-called algebraic n-torics. This is an n-fold product of copies of Cx being the units of the ring C. And this is a set of all P and C, and I have all coordinates being non-zero. So under a more generous definition of algebraic variety than the one that I started with, this counts as being an algebraic variety, and it's also a multiplicative group, so it's an algebraic group. So an affine toric variety is an irreducible algebraic variety V containing some sort of subvariety W, such that V minus W is going to be an algebraic n-torus, where n is the dimension of the variety. And this torus acts on V by coordinate wise multiplication. So you think of n tuples of points, then there's a corresponding torus action that acts coordinate wise as like left multiplication on each of the coordinates of your point. So considering the domain R equals CV, this is going to be a normal toric ring, or it's also called a monomial ring in some papers. And IV is called the toric ideal. So it's prime and generated by binomial relations. And we'll also assume that R is a normal ring. So if you have a monic non-constant polynomial, F inside of Rx, and that has a root B inside of the fraction field of R, then B actually belongs to R. So that's the relationship for normal. So we're interested in normal affine toric rings. And that's the main case that we study inside of the thesis. So I think of toric rings as polynomial rings in the Inception, like the movie. So here I'll take an n-tuple of non-negative integers, b, and a can be an integer n-tuple. This always yields a Laurent monomial, and you can think of that as a function too. And there's this fundamental relationship between the exponent vectors and products of Laurent monomials. So the polynomial ring R has a C vector space basis consisting of all the standard monomials and B running over all of these n tuples B. And when you consider a toric ring, you consider a different list of algebra generators. And this has a C vector space basis of monomials running over all B inside of the non-negative integer tuples. So with 4, we would be considering maybe variables inside of the parentheses and considering standard monomials in those, but we're now thinking, we're incepting these Laurent monomials, and there are L with them. And then we consider these relationships in terms of more general Laurent monomial notation. But yeah, so you can think about toric rings being sort of like polynomial rings, but there might be relations that you have to consider. So we'll let S and D consist of all of the points A whose coordinate sum to D being at least 1. And we can consider the Dth Veronese subalgebra of this polynomial ring, and it's a normal toric ring consisting of the generators being these Laurent monomials where the A value sums to D. And these are some examples where we worked first in 2 variables with D equal to 4, and then working in 3 variables with D equal to 2. So these are some examples of these Veronese subalgebras. So these are pretty basic examples as far as the monomial ring notation. It turns out that when you work with toric rings, normal toric rings, then there's a way to relate to convex geometry, how you build the ring. So here I have a cone C with the parameter D being greater than 2. And then there's a fundamental Zonotope inside of C, consisting of taking various line segments and then considering the Minkowski sum of them and getting a Zonotope. So in this case, there's 2 special points, and we can consider the Zonotope of C being determined by line segments along each, essentially each ray. So I should define what strong convexity, rationality, and codimension are. So strong convexity just means that the cone doesn't contain any positive dimensional linear subspace. So the 0 vector is the only one that's allowed to be in there. Rationality just means that the rays that generate the cone are generated themselves by lattice points. Cone dimension, you take all of these lattice points, one from each ray, and you consider the vector space that's generated by all of those lattice points. And that is the cone dimension. So in this case, the dimension would be 2. And primitive ray generators, you want ray generators such that the GCD of the coordinates is 1. So no common prime factor. And for us, all cones are strongly convex. rational, and full dimensional. This turns out to be the nicest case in which to think about these normal toward rings. So yeah, this zonotope is basically you find a primitive generator for each ray, and you draw the this Minkowski sum of the line segments between 0 and the element, the primitive ray generator, and you do that for all of them, and that's Zano C. In this special case, the yellow points are a leanest possible generating set for the semigroup of lattice points inside of C, and the relation is vector addition. So it turns out that this semigroup is always finitely generated by some list of lattice points by the lattice points inside of P. And often there's a most efficient generating set. And we call that a Hilbert basis. And in this case, it's the points in yellow. So for reference, we have these points in yellow inside of this sonotope. And what we can do is consider that each lattice point inside of this semigroup yields a monomial function in terms of n variables. And these form the vector space basis of the normal toward ring that corresponds to C intersects the n. So we consider that relationship in the picture on the left, and we get those Laurent monomials in terms of S and T. And it turns out that this construction will give you a Veronese subring essentially in 2 variables, a Veronese subalgebra in 2 variables. But yeah, this is just a really nice example where the behavior was nicer than the general case. I'll say conversely that any normal toward ring can be built according to this formula in terms of convex geometry. And one thing I'll also mention is that CV or C check is the collection of real n tuples such that when you dot product with, it should be C. When you dot product with the values of V that are in C, you get that dot product is non-negative. Okay. So again, this main theorem is that there exists a D depending only on the ring structure such that P symbolic Dn is contained in Pn for all n and all monomial primes P and R. So the linear algebra recipe for this is you consider the variety corresponding to your cone C, and we'll consider the coordinate ring, instead of looking at C intersects N, we'll look at C check intersects N. This coordinate ring can be cooked up from a cone G, where G consists of primitive ray generator. And you can have CV equals cone of H, where we're talking about primitive ray generators. And really in the case of H, we'll take the Hilbert basis. And if you do that, then what you can do is you can sum together all of the primitive ray generators inside of G and to get one vector, and then dot that with each member of the Hilbert basis for the dual cone. And in that case, you get a positive integer, and that positive integer does the trick. So you can go from the convex geometric data to building, in terms of essentially linear algebra, value of D that works for your coordinate ring R. So this is something that you could, like, for instance, study in a computer algebra system like Macaulay 2. So We'll revisit the Veronese example. So this
Ask a
is the
question.
cone. Yes?
I just in the statement, the H, you said it was the primitive generators of the rays of the cone, the dual cone. But do you have to take, I think you said like Hilbert basis, do you have to take generators for a semi-group, or can you just take the generators for the cone?
For the dual cone, it's important to include generator or semi-group generators that are not necessarily the primitive ray generators. That could be larger. So yeah, that's sort of a typo in the statement.
That's okay, yeah.
But yeah, H is going to consist of all of the Hilbert basis vectors, including the ones that aren't necessarily attached to a ray.
Right, thanks.
Yeah, so this cone CEN consists of mostly the standard basis vectors and then one other vector. And its dual consists of one standard basis vector, En, and then a certain expression in terms of the other EI. So the toric ring that you get actually can be shown to be isomorphic to the ETH Veronese subring of this polynomial ring. And when we go to check out dV, we can do the arithmetic and then get E back. So in this particular case, the degree of your Veronese subalgebra turns out to be the dV. And in 2017, Dow, Stefani, Grifo, Hunicke, and Nunez Betancourt, a team of 5 commutative algebraists, they showed that if you consider your ring to be the ETH Veronese subring of this polynomial ring, then you get this symbolic and ordinary power containment for all R and all prime equals P. And they show that you can take dr to be E times, it should be little n minus 1. E times little n minus 1. So for instance, you could consider that where n has at least there are at least 2 complex variables. And then that's what the result is. So for this example, depending on how much of a number theory nerd you are, you might care to know why I chose these numbers. 28 is the second perfect number in number theory. All the sum of its divisors is the same as twice the number itself. You may have heard about this show called Are You Smarter Than a Fifth Grader? Well, this is a show where you could win $1 million if you solve a 5th grade question at the end of doing a bunch of other questions. And one time the question was 5th grade math, and it was just list all of the positive divisors of 28, and the contestant listed all of the non-unit divisors and used the number 1. And so it went down from $1 million to $10,000. So in deference to that, I can list all of the non-unit positive divisors of 28, the ones that this guy listed. 1729 is the so-called Ramanujan Hardy taxi cab number. This is explained in the movie, The Man Who Knew Infinity. And 10,000 or 14,641, that's just the largest power of 11 that looks like the corresponding row of Pascal's triangle. So given the J between 1 and 1729, we can consider a corresponding Veronese subring, and then consider the tensor product of all of these Veronese subrings. And then we in turn consider the normal toric ring T that's a given tensor product of these TJ rings. And it turns out that when you compare a few different results in my thesis, you can get that 28 serves as a uniform multiplier D for a bunch of the monomial primes and other things inside of this ring. So for the monomial primes, this is a ridiculously large power of 2. And all primes of height 1 will have this relationship that relates to the divisor class group construction. for these rings. And there's an infinite number of primes of height at most 8645, I can say, that will also satisfy this containment using a different result in my thesis. But yeah, this is a lot of data, is the point. With the large power of 2, you might as well think of it as almost like infinity. But yeah, that's pretty much it for my talk. I thank Karen Smith, my advisor, for pointing me in the direction of this problem for my thesis, even though most commutative algebraists consider symbolic powers to be very scary objects. I thank the Michigan Math Department for housing this research. NSF for the Graduate Research Fellowship I was on while working on this stuff. The organizers of this seminar, and everyone who attended the talk. And if you have any questions, bring them on. I'll try to answer them.